Part C. The satellite transmits polarized microwaves back to the Earth. State a typical wavelength for microwaves. So microwaves, if you remember the microwave we used in the microwave transmitter we used in the classroom has got a wavelength of 3 centimetres. And so that's 0.03 metres. But they will actually allow you anything between 10 to the minus 3 up to 10 to the minus 1 metres. Microwaves are transverse electromagnetic waves. Explain what is meant by transverse. Transverse means that the vibrations are only confined to one plane. Sorry, I'm answering the wrong question there. This is actually the answer for polarised, so we'll just swap those two around. So a polarised wave there, the vibrations are only confined to one plane. And down here I'm going to explain what a transverse wave is. So this is the polarised. Just be careful about that if you're looking at it. And then what is meant by transverse. So a transverse wave is one where the vibrations of the particles are perpendicular or right angles to the direction of the travel of either the energy or just of the wave itself. Part 4. The satellite is 3.6 by 10 to the 7 metres above the Earth's surface. Calculate how long it would take a signal transmitted by the satellite to reach a point on the surface directly below the satellite. So you can just use speed as distance over time. And the speed, of course, of the signal is 3 by 10 to the 8, which is the speed of light. So time is distance over speed. 3.6 by 10 to the 7 over 3 by 10 to the 8. And that gives you a time of 0.12 seconds. And you would expect a fairly short time. The last question. Explain what is meant by total internal reflection. This is part D. So when light is reflected back at a boundary, is really what happens there. So if you have light coming from a dense medium to a less dense medium, and it's refracted away from the normal till it passes its critical angle, then it's totally internally reflected. The best definition of that is if you have light travelling from a material of high refractive index to low refractive index, at an angle greater than the critical angle. Then it is reflected back into the high refractive index material. Instead of being refracted. Into the low refractive index material. And that's really what that's what total internal reflection is. Last part is about the endoscope. So this is where you have total internal reflection, where you have light being reflected the whole way down a narrow optical fibre. The endoscope makes uses of bundles of optical fibres. One of these bundles is coherent, the other is non-coherent. Explain the meaning of these terms in this context and describe the use of each of these bundles. So coherent is where the fibres have the same order. In the mark scheme they actually say parallel arrangement, which is quite a good way to explain that. Parallel arrangement. So the same order at each end. And then non-coherent is obviously the opposite of that. Fibres don't have the same order. Now that doesn't necessarily mean that they are tangled, and you might be careful about using that word, don't have the same order. Or you could say that they are non-parallel. And the last part, describe the use. So the coherent bundle is used to transmit light from the image so the image can be viewed clearly and in the correct order. And then non-coherent is just used to illuminate the part of the body. And it doesn't matter what order the fibres are in, because you just want light from the outside to get in. So it's used to illuminate the part of the body being investigated.